For question 15, we have a common collector amplifier. Okay. Part A, again, draw the small signal equivalent circuit, then um, derive an expressions uh, for the input resistance, output resistance, and the overall voltage gain. And also for part C, we have to compute those values and then what would be like a suitable application for this circuit. So remember that for small signal, we have the capacitors as a short circuit. So this one here, short circuits. This one here goes again to the ground. This one here becomes also a short circuit. Okay, so the small signal circuit would be just the source, small signal source here, Vs, its resistance, right? Then we have R1 here, R2 here, and then we go to the T model. Okay, so we have base here, we have RE, and if we go up there, there's a short circuit here, right, that connects the load now also to the emitter. So the emitter terminal that we have here, now we have the emitter resistance, RE, but we also have the load, RL. And then up here we have the current source, and then the collector that is grounded. So this is alpha IE, this is IE. Okay. Now for part B, because we know the values of these small, so we know RE, we are supposed to use the output resistance as infinite. So we basically know alpha and RE, we don't have to calculate them, it's already given by the problem. We just have to figure out what would be like the input resistance. So let's analyze the circuit. So for this input resistance is the resistance seen from this terminal here, right? So we already have R1 in parallel with R2, but then again, we can't do that in parallel with RE in series with the parallel of RE and RL, because we have here at the base this alpha IE connected. So one thing that we can do is reflect this series of the small signal RE and the parallel between RE and RL to the base, right? So then we would have the parallel. So it would become something like this. So we have R1 here, we have R2 here, and then we reflect that to the base, right? But then the base gets connected directly to the ground, right? So this one here, this resistance here, it's the resistance that is being reflected. So this is R1, sorry, and this is R2. And then the input resistance seen from this terminal. So this R here, it's going to be the reflected series. So it would be RE, sorry, yes, so it's RE in series with the parallel of RE and RL. And then to reflect this entire thing here to the base, we multiply by beta plus 1. And then we solve this parallel between those three resistances. So overall, this input resistance, so again, B and C, right? Input resistance, it's 6.49 kilo ohms. Now for the output resistance, okay, which would be the resistance seen from this terminal here, right? Then we have to reflect this RS, R1, and R2 to the emitter side. Okay. So overall, the resistance that we would see if if Vs is equals to 0 would be just Re. Okay. In parallel with the series of Re plus, it's basically Rs in parallel with R1 in parallel with R2, but then reflected to the base. So it would be this, so it's Rs in parallel with R1 in parallel with R2, but now to reflect from the base to the emitter, we have to divide it by beta plus 1. And that would be something like we have the base here, right? So the base, we have Re, and we are basically reflecting Rs in parallel with R1 in parallel with R2 to the base. So we would add this one here, and this is Rs in parallel with R1 in parallel with R2. Everything here divided by beta plus 1, okay, because we reflected that. So this one here goes to the ground, right? And then remember that we are seeing the resistance from this terminal here, right? So this goes to the ground. This is Re. Here we have RL. So it would be the resistance in from this terminal, okay? Which is just Re here in parallel with Re plus that resistance that we had connected to the base, but now reflected to the emitter. So this output resistance, it gives us 11.31 ohms. So it's a very small output resistance, which is desired for this kind of um, amplifying circuit. Now, for the overall voltage gain, again, we can split that into two. So it's just going to be Ri divided by Ri plus Rs, again, and that's equals to 0.984. Usually for a very small source resistance, Rs, this AV1 would be close to unity, right? And then AV2, it's going to be the parallel between Re and RL divided by the small signal Re in series with the parallel of Re and RL. And this is something that would be close to unity too. So it's 0. In our case, it's 0.9411 volt per volt. And then if we multiply both AV1 and AV2, we get something that it's 0.92689 volts. Okay, so you see here that the unity gain is 0.9860. So the overall voltage gain, sorry, it's close to unity, 0.98, right? And we also see that it has like a very high input, it's a high input impedance compared to the other topologies that we have seen, right? So we have a high input resistance, we have a low output resistance, and we have a gain here that's close to unity. Okay, so overall this kind of circuit, it would be suitable for a voltage gain, for a voltage buffer. Okay, it can provide like isolation, so it basically can isolate the input circuit with the output circuit. It could also be used for impedance matching circuit or like more resistor matching circuit. And also it could also be used with as a switching circuit because it also have like a high current gain. So those are kind of applications that we have, but mostly for a voltage buffer. So this is basically it. So let me just write here as a voltage or say follower, but buffer. Okay. So this is all for this problem.